So last but not least, I would like to introduce the final speaker for this session. So Professor Xiang is actually a professor here at Zhejiang University, but before coming back to China, he had his own journey. He was a PhD student at McMaster University and then did a postdoctoral fellow in Professor Barton's group at MIT. And then he joined actually Queen's University, Canada. And recently, actually last year, he came back home in Xiang University. So welcome back to your university and looking forward to your talk.
Thank you, Professor Maranthi, nice introduction. And actually, my mind is still with Professor Ricardo's presentation because I just realized his presentation is highly related to mine. The reason is I will be going to talk about piecewise linear approximation, and we know that piecewise linear approximation will lead to problems with other discrete sets. Yeah, so I'm still considering maybe Dr. Ricardo's method can help us in the future. Let me start with the problem, the motivation of this research. So in this workshop, we have seen a lot of model-based methods, and most of the methods require that we solve a difficult optimization problem, and usually the problem includes complicated physical-chemical relationships that makes the problem non-convex. Now in a lot of situations, the problem has poor local solutions, which means if we use traditional local solvers, we will have very bad solution. And on the other hand, if we use global solvers like Barron or Skip, we will have to spend a lot of time that we can't really wait for several days for a solution. So this motivates this idea of piecewise linear relation for kind of balancing the precision of the model and the solution efficiency. Now, piecewise linear approximation of a complex system is not a new idea. It's been in industrial practice for many years. But I think in this new century, there has been growing interest in developing high precision piecewise linear approximation for reliable optimization. So one direction is to develop reliable piecewise linear approximations so that we have a reliable theoretical model, which is easier for computation. The other track of research is to use piecewise linear approximation to generate tight bounds for global optimization, so as to improve the global optimization efficiency. So both research directions sort of enjoy the maturity of the modern MILP solvers, and hopefully in the future we will be enjoying the special order discrete sets idea to improve the solution. But the key here is not so our focus here now is not the solution method for now, it's more toward how do we generate piecewise linear approximation with guaranteed precision. This brings the idea of CPWL Delta-Approximator. So basically, we want to make sure the piecewise linear approximation we generated is precise enough for the given search domain. Okay, so not just precise on discrete points, but it's precise enough over the whole search domain. Now, so there are several challenges here. One is that how do you guarantee precision over the whole domain, right? And how do you achieve efficient piecewise linear approximation in terms of reduce the number of pieces you need, because the number of pieces is related to the size of the MILP problem you're going to solve, and how do you determine the size of each piece in an optimal way. And finally, if you have multivariable functions, how do you define a piece? A piece should be a squared box area or a triangular region or whatever, right? So what is the best shape of a piece? So for the first two questions, I think it has been addressed in terms of the univariate CPWL delta approximation research. I think this is a solved problem. So people have developed a framework that can guarantee a delta approximation precision being guaranteed over the whole such domain. Basically, you do that iteratively. Like you use sample points from the domain, and and then you fit CPWL function for the points over the sample data set, and then you see if the existing CPWL is good enough or not for the entire domain. If not, then we keep adding the points into the set. Now this process is guaranteed to be terminated in finite number of steps. Okay. Now, but the question will become more difficult to answer if we have multivariable functions, because we don't know what should be the ideal piece for each piece of the piecewise linear function. For example, for the simple example, you could use the classical triangulation method, okay, to divide the domain into triangular subregions. This is a classical method in the literature. Now, but actually, later on we will see we have a better method to actually reach a different shape of partitioning, which is to partition a domain to more like squared subdomains. Okay, but on the other hand, if you have a different function, maybe the squared, the box subdomain may not be better than triangular domain or some domain with other shapes. Right? So now we need a generic approach to decide the best ideal shapes of the pieces of each subregion for a CPWL function. So then we came up with this very different idea. Okay, so we are not trying to predefine the shape of each piece. Okay, we are trying to represent a piecewise linear function as the difference of two convex piecewise linear functions. Okay, so there is a theorem in the literature that any piecewise linear function over a compact domain can be represented by the difference of two convex functions. Now, each convex part of the piecewise linear function can be easily represented by the maximum of a set of f(n) functions. So here you don't have to predefine the shape of the subregion you're going to use. Okay, so because the pieces are determined implicitly by the maximization operation. So we call the positive part to be the positive DC component, and negative part to be the negative DC component. Now the advantage of this idea is more clear when you have multivariable functions. So this is an example of two variable function. This bilinear function and the original function has this curve, right? So we could generate a piecewise linear function that approximates the original bilinear function. Now this function, the pieces is not defined, not predefined, right? It's actually, this is generated by the difference of two convex piecewise linear functions, and each component is determined by the maximum of a set of f(n) functions. Okay, so with this idea, and with the converging flow chart that has been applied for single variable univariate functions, we can systematically generate piecewise linear functions with guaranteed precision for functions of any dimension. Okay, so now the key part of this process is to, at step 2, we want to fit a difference of convex continuous piecewise linear function that achieves the predefined precision on the sample data set. So that step is the most difficult step, and I'll explain that in the next slide. So this step is difficult because when you fit the function to the data set, you will have to handle this maximization operation. Right? You have to handle that. So this is a non-smooth function. So basically, there is no good solver to directly handle maximization operation. So a natural way to do that, to handle that function, is to use integer variables to sort of describe the logic behind the maximization operation. So basically, you want the function to be greater than or equal to any f(n) functions in the maximization operation. But then for the maximum, for a point at which the one fn function will have the highest level, right? So you decide the highest fn function by this integer variable z, and only one of them, right? Among all the pieces, only one of them reach the highest level, and that will be the surface of the maximization operation, the function defined. And this is a mixed integer optimization problem, and hopefully this can be solved efficiently by this idea of special ordered discrete variables. We haven't tried that before, but if we don't use that idea, actually this can be very slow for difficult functions. So that's why we have thought about this, how do we solve this problem more efficiently. Then we came up with a better approach. So we don't solve this problem directly. Okay, so we're trying to formulate the fitting problem into a linear program problem. Because of the time limit, I don't have time to explain the full logic behind this reformulation. But basically, what we do is we are simultaneously deciding two sets of piecewise linear approximation. One we call it a full order piecewise linear approximation. This is like a reference model for us, and we don't want to use that. We actually want to use a reduced order piecewise linear function by solving this linear program problem. And the reason why we can avoid this integer variable is because we pre-assign different points to different fn functions in the maximization operation. Now, this one, we have an initial guess, right, for this assignment set. If our initial guess is correct, then we're done. And after solving the LP problem, we're done. But if our initial guess is wrong, then we'll update it. Okay, so you can prove this process is finite. Okay, so we solve a sequence of LP problems. If we are lucky, then we don't have to solve too many, and before we reach our optimal solution. So this is the LP approach. Then we try this approach on different approximation problems, and we realize sometimes it works fine, but for more difficult problems, it's still not good enough. And the reason is we have many linear constraints, because the number of linear constraints are related to the number of data points in the sample set. So now, in order to make this approach more accessible for applicable for difficult problems, we're trying to reduce the problem size by removing some of the constraints here, because some of the constraints here are never active at the solution. So that motivates the next idea of using, we call that the relaxed LP method. So in this method, we don't consider the full set of equations in the LP approach. We only consider a subset of them, and then we keep updating these subsets. So we call these constraints lazy constraints. So they don't participate in optimization unless they're really needed, right? So we keep updating the lazy constraint set until it converges to the optimal solution of the previous LP problem. And this process is also finite. Okay, and now we have the computational tool. So we can actually, with these methods, we can practically generate piecewise linear approximations for certain functions. Okay, so these are some examples for two variable functions. And you can see that these functions, the domain of the function are partitioned into polytopic subregions of different shapes. Okay, so if you predefine the subregions to be triangulars or boxes, you won't get the most efficient partition. Okay, and this is a three-variable function. So here the domain is in a 3D space, right? So actually for this function, if you have this approximation error, then you would partition the domain into these subregions, right? So you would never imagine these subregions should look like these until you really solve that problem. And this is achieved by this BC idea. So for each component, actually, we don't need that many subregions, right? For the positive side part, we only need 2 partitions, and for the negative part, we only need 3. But they combine together will generate more pieces. Okay. Now, then if we try more and more variables in the function, we'll see the computational time increase dramatically. So here is some computational results. We try functions with n variables, x1 times x2 onto xn. So if you have 3 variables in the problem with different precision requirements, okay, you will have a different solution time. So we can ignore the number in the middle because they're not relevant to the focus of this talk. So basically, the LP method is not as good as the relaxed LP method, except one situation, which is probably here. Yeah. So most of the time, the relaxed approach wins. Okay. And the reason is we relax the problem such that a lot of redundant constraints can be removed during the solution process. And now we are still working on in this areas, and hopefully next year also we will be able to solve variables functions with 10 variables. Okay, so now we are only able to solve a problem with 5 variables, but I think there is still room to improve in this approach. Now, next I will introduce one way to apply this idea, the delta-approximator idea. So I believe there are many different ways to utilize this result, but we have found one way to utilize this result for non-convex optimization. So this is let's assume we have a non-convex function and we already have a delta approximator for it. So now, if we move the piecewise linear function up by delta, we're guaranteed to have an overestimator of the original function, right? Because we know the precision is the maximum error is delta. So if we move the function up by delta, definitely we will have an overestimator. And similarly, if we move it down a little bit, we will have an underestimator. And also, if we have a very precise approximation, so when delta is very small, actually the over and upper over underestimators are actually approximators, right? So there's not much difference. So this is different from convex relaxation in global optimization, where your relaxation could be very different from the original function. But here, the relaxation actually, the trend are pretty much the same, as long as the delta is small enough, right? So then we can utilize this feature to design some efficient solution approach for difficult problems. So here we are interested in solving real-time non-convex nonlinear optimization problems, such as some planning problem or a real-time optimization problem, and so forth. So we do have these kind of applications, many applications in the industry. So we say these problems have to be solved online repeatedly. Right? So when the price or demand change, then we have to solve the problem with the same structure again and again. Okay, so we can construct a lower bounding problem using that idea, right, offline. And then in the real time, we solve this lower bounding problem as the first step. So we solve the problem in the real time in 2 steps. 5 minutes. So the first step, you solve this relaxation problem. And it's also an approximation problem because the solution is expected to be very close, right, to the optimal solution of the original problem if delta is small enough. So, and this lower bounding problem gives you a lower bound, gives you a sense how best you could achieve. And then you solve the original problem using local solver like CONOPT or whatever, local solver, IPOPT, and using a local solver, right? So, and then use the solution from the MILT problem. As I said, this problem, on the one hand, it's a lower bounding problem. On the other hand, it's a good approximation of the original problem. So then we will have a good local solution. So if delta is small, then most of the time the local solution is global. It's globally optimal. So I'm going to show an example. This is some sort of preliminary results that we have. This is an operational problem for optimizing the operation of a natural gas transmission network. So we have compressor stations and we have pipeline flow and pressure relationship. So they're complicated. The most complicated part is the compressor station performance model And this is the piecewise linear approximation approach, the method that we have used to approximate the complex performance model. So the original model is defined by a set of nonlinear equations, which is very non-convex. But now we can just use piecewise linear functions to describe it. And then we tried two different solution methods. One method is just to use a global solver to solve the NLP problem directly. And the other approach is to use Groby to solve the lower bounding problem, and then use the solution, refine the solution with count, and we'll see what happens. And we also tried 16 scenarios because we are considering operation problems. We want to see how the solution approach performs over different scenarios. So when you use Barron, for all the scenarios you can, so they can converge, right, to a good with a good optimality gap within the time limit of 1 hour. So it's always about 10%. Optimality gap is always about 10%. But if you use the piecewise linear approximation approach, you will actually, when you have the delta to be 5 or 8%, you already have a pretty good result. Because we know the optimality gap, right? Because we solved the low one problem. And when the delta is small enough, actually the solution quality is really, really good. While at the same time, the solution time is only half a minute, which is acceptable for practice. And the standard deviation is also low. So it's pretty robust in terms of the different scenario condition. So as the summary, we think piecewise linear delta approximators are good surrogates, and we can use that, definitely use that for non-convex optimization. And this is ongoing work, and we're trying to make the generation process more and more efficient. And on the other hand, we are trying to find more applications to show the benefits of this result. And there are a number of references related to this work. And that's all. Thank you.